Let's continue. Let me open the table of content first. Okay. We are on chapter 20, patching smaller tables. And previously we checked out this one, simple solution picker table, and now we will check hybrid approach, patching and segment. Let me open that. Okay, right, basically this is the, what is it? The problem that, or the question that we want to answer. The problem is something like this. The patch cable can be big, and every process have their own patch table. So yeah, it's gonna be a lot of memory usage if we didn't decrease the patch table size, I guess. Okay, simple solution, bigger patch, so each patch have a big patch size, right? Something like this, and it can decrease the patch table size, something like that. But the problem is internal fragmentation. Big patch lead to waste within each patch. So we might not be able to use all the memory within one patch if the patch too big, which cause the internal fragmentation. The waste is internal to the unit of allocation. Something like that. Application thus end up allocating bits but only using little bits and piece of each, and memory quickly fills up with these overly large bits. Okay, thus most systems use relatively small bit size. In the common case, at 4 kilobyte as in x86 or 8 kilobyte as in SPARC v9, our problem will not be solved so simply unless, right? And from the aside, it looks like we can have multiple page size, so not only one page size like 4 kilobyte for example, but we can also have different page size too. It is interesting. A single large page can be used for a specific portion of the address space, enabling such application to place frequently used and large data structure in such a space while consuming only a single transaction look aside buffer entry. Right. This type of large page use is common in database management system and other high-end commercial application. High-end commercial application. Okay, the main reason for multi-page size is not to save page table space. However, it is to reduce pressure on translation look aside buffer, enabling a program to access more of its address space without suffering from too many TLP miss. However, as researchers have shown, using multiple page size makes the operating system virtual memory manager notably more complex, and those large pages are sometimes most easily used simply by exporting a new interface to application to request large page directly, right? Okay, using multiple page size makes the operating system virtual memory manager notably more complex, so the application can request large page directly rather than letting the operating system manage that. Maybe something like that. Okay, now let's read this one. Hybrid approach, batching and segment. Whenever you have two reasonable but different approaches to something in life, you should always examine the combination of the two to see if you can obtain the best of both worlds. We call such a combination a hybrid. Okay. The combination of the two to see if you can obtain the best of both worlds. We call such a combination a hybrid. For example, why eat just chocolate or plain peanut butter when you can instead combine the two in a lovely hybrid known as the Reese Peanut Butter Cup? Okay, years ago, the creator of Multics, in particular Jack Dennis, chanced upon such an idea in the construction of the Multics virtual memory system. Specifically, Dennis had the idea of combining batching and segmentation in order to reduce the memory overhead of page table. We can see why this might work by examining a typical linear page. Dennis had the idea of combining batching and segmentation in order to reduce the memory overhead of page table. We can see why this might work by examining a typical linear page table in more detail. Assuming we have an address space in which the used portion of the heap and stack are small. For the example, we use a tiny 60 kilobyte address space with 1 kilobyte page. Figure 2.1. The page table for this address space is in figure 2.2. 2.1. Where? Oh, is this one? Okay. Assume we have an address space in which the used portion of the heap and stack are small. Okay. The page table for this address space is in figure 2.2. Okay, this is figure 2.1. A 16 kilobyte address space with 1 kilobyte page size, something like that. Okay, virtual address space, physical memory. Alright. Okay. Figure 20.2, a page table for 16 kilobyte address space. Page frame number, valid bit, protection bit, right? Or we can also call that permission, I guess. Present bit, and then 30 bit here to indicate if the page has been changed or not. Maybe something like that. Okay. This example assumes the single code page virtual page number 0 is mapped to physical page 10, the single heap page virtual page number 4 to physical page 23, and the two stack page at the other end of the address space. Virtual page number 14 and 15 are mapped to physical page 28 and 4 respectively. As you can see from the picture, most of the page table is unused, full of invalid entries. What a waste. And this is for a tiny 16 kilobyte address space. Imagine the page table of a 32-bit address space and all the potential waste space in there. Actually, don't imagine such a thing. It's far too gruesome. Okay. Alright. Thus, our hybrid approach, instead of having a single page table for the entire address space of the process, why not have one per logical segment? Okay. Our hybrid approach, instead of having a single page table for the entire address space of the process, instead of having a single page table for the entire address space of the process, why not have one per logical segment? Oh, having a single page table for the entire address space of the process, why not have one per logical segment? Okay, in this example, we make those have 3 page table, one for the code, and then heap and stack part of the address space. Oh. Okay, interesting. Have one page table per logical segment. Okay. Now, remember with segmentation, we had a base register that told us where each segment lives in physical memory, and a bound or limit register that told us the size of said segment. Okay, base register that told us where each segment lives in physical memory, and a bound or limit register that told us the size of said segment. Okay. In our hybrid, we still have the structure in the memory management unit. Here we use the base not to point to the segment itself, but rather to hold the physical trace of the page table. Okay. The base not to point to the segment itself, but rather to hold the physical trace of the page table. of that segment. The bounce register is used to indicate the end of the page table. That is how many valid pages it has. Oh, how many pages it has? Okay, interesting. Let's do a simple example to clarify. Assume a 32-bit virtual address space with 4 kilobyte page and an address space split into 4 segments. We will only use 3 segments for this example. One for code, one for heap, and one for stack. Okay. 32-bit virtual address space with 4 kilobyte page size and an address space split into 4 segments. Right. We will only use 3 segments for this example. Oh, okay. So we split the address space into 4 segments, but we are not using those 4 segments. We only use 3 segments, something like that, to determine which segment an address refers to. Which segment an address refers to? We will use the top 2 bits of the address space. Let's assume 00 is the unused segment with 01 for code. Oh, okay. 10 for the heap and 11 for the stack. Thus, a virtual address look like this. Okay, this is the unused segment from the 4 segment here. Okay. Okay. What is this? Is this the combination? Right. What is the number above here? Represent. Okay, let's continue first. In the hardware, assume that there are those 3 base or bounce pair for each three base or bounce pair, one each for code, heap, and stack. When the process is running, the base register for each of the segments contains the physical address of linear page table for that segment. Wait a minute. Yeah, I'm not sure what this means. What is the number above here and what is the number below here? Is this the segment? Segment 0, 1, 2. Okay. Yeah, I'm not sure yet. Maybe we will get the explanation later on. When a process is running, the base register for each of these segments contains the physical address of a linear base table for that segment. Thus, each process in the system now has 3 page tables associated with it. On a context switch, this register must be changed to reflect the location of the page table of the newly running process. On a context switch, this register must be changed to reflect the location of the page table of the newly running process. On a TLB miss or translation look aside buffer miss, assuming a hardware managed TLB, that is where the hardware is responsible for handling TLB miss, the hardware uses the segment bits to determine which base and bounce pair to use. Okay. The hardware then takes the physical address therein and combines it with the virtual page number as follows to form the address of the page table entry. The hardware then takes the physical address therein and combines it with the virtual page number as follows to form the address of the page table entry. Okay, the hardware then takes the physical address therein and combines it with the virtual page number as follows to form the address of the page table entry. Alright, virtual address. I guess this is segmentation marks. Right shift with the segment bits. Okay. We got the segment bits here. Then this one only highlighting the virtual page number and then shift to get the virtual page number. Address of page table entry, the segment bits plus virtual page number multiplied by the size of page table entry. Okay. Which base and bound pair to use? The hardware then takes the physical address therein and combines it. Oh, okay. Takes the physical address therein and combines it with the virtual page number as follows to form the address of the page table entry. Okay, so from this virtual address, we take the segmentation or the segment bits here, and then after that we take the virtual page number and then combine that, okay, to get the address of page table entry. This sequence should look familiar. It is virtually identical to what we saw before with linear page table. The only difference, of course, is the use of one of 3 segment base register instead of a single page table register. Instead of the single page table base register, right? We use this segment base register. Okay. Let me read this. The critical difference in our hybrid scheme is the presence bounce register per segment. The critical difference in our hybrid scheme is the presence of a bounce register per segment. Each bound register holds the value of the maximum valid bits in the segment. Each bound register holds the value of the maximum valid bits in the segment. Okay, is the presence of bounds register per segment. Each bound register holds the value of the maximum valid bits in the segment. The value of the maximum valid bits in the segment. For example, if the code segment is using its first 3 bits, 0, 1, and 2, the code segment table will only have 3 entries allocated to it, and the bound register will be set to 3. Okay. Memory access beyond the end of segment will generate an exception and likely lead to the termination of the process. In this manner, our hybrid approach realizes a significant memory saving compared to the linear page table. Our hybrid approach realizes a significant memory saving compared to the linear page table. Unallocated bits between the stack and the heap no longer take up space in a page table, just to mark them as not valid. Okay, however, as you may notice, this approach is not without problems. First, it still requires us to use segmentation. As we discussed before, segmentation is not quite as flexible as we would like, as it assumes a certain usage pattern of the address space. If we have a large but sparsely used heap, for example, we can still end up with a lot of page table waste. Second, this hybrid cause external fragmentation to arise again, right? While most of memory is managed in page size unit, page table now can be arbitrary size. In multiple of page table entry, thus finding free space for them in memory is way more. Thus finding free space for them in memory is more complicated. For this reason, people continue to look for better ways to implement smaller page table. Alright. Okay, the tip use hybrid. Okay. Oh, hello. Nangataku. You remember me? I don't think so. Okay. Yeah, maybe we've talked in the chat before. But yeah, don't really remember, I guess. Simulating scheduling algorithm would be fun. Simulating scheduling algorithm. Oh, the scheduling algorithm is on the early chapter here. I mean, there is this homework simulation, right? So we can take a look at that. Previously I've taken a look at this too. So there is that. Honestly, I'm more interested in the memory management here compared to the scheduling. But again, it is subjective, I guess. Okay, tip. Use hybrid when you have two good and seemingly opposing ideas. You should always see if you can combine them into a hybrid that manages to achieve the best of both worlds. Hybrid species, for example, are known to be more robust than any natural occurring species. Oh, I didn't know that, I guess. Than any natural occurring species. Of course, not all hybrids are a good idea. See the Sidong or Sonki, which is a cross of a zebra and a donkey. What? Is this exist? A cross of zebra and donkey. If you don't believe such a creature exists, look it up and prepare to be amazed. You know what? I'm curious. Sonki animal. Let's see if it is exists. Like what? Oh, okay. It exists. Wait. Oh. Okay. Oh, interesting. Okay, a sonki is a hybrid animal resulting from the mating of a zebra and a donkey. The term sonki is a portmanteau of its parent species. What is portmanteau? Portmanteau, I guess. Portman. Okay. I'm not sure if that is correct translation. I'm assuming this is something like combination of its parent species. Typically the sire is a zebra and the dam is a donkey. Though the reverse cross can also occur. This genetic pairing produces an animal that inherits traits from both parents, creating a mosaic of characteristics that are both familiar and exotic. Okay, these hybrids are part of a broader category known as zebroids. There's a category called zebroid. Oh, okay. Which includes any cross between a zebra and another equine. Wait, what is equine? zebra and another equine, such as a source. What? Zebra and horse, and a zony, zebra and pony. Well, today I learned something new, I guess, other than operating system. Oh my god, like why? Yeah, that make me curious why we are trying to cross zebra with another equine species. Yeah, that interesting. A coat of many stripes appearance. Where the wild things aren't usually fitted in distribution. Okay, well, let me put this in the chat, I guess, in case anyone wants to take a look. Hello, Sam Roti. Good to see you, man. Okay, alright. Yeah, we are still learning about operating system and reading. Okay, we are in the chapter 20, learning about patching smaller tables, basically trying to find a solution to reduce the patch table to save the memory usage, something like that. And I'm reading about this tip about use hybrid, right? Basically combine multiple option and so that maybe we can achieve the best of both worlds, something like that, right? And then suddenly I found out about this Sonki or Sitong, which is a cross of zebra and a donkey, and it is actually exists, this one. They have the stripe of zebra and the donkey form, I guess, or maybe the opposite also true. And it is not only zebra and donkey, but there are also another cross between a zebra and another equine, such as a horse, zebra and horse, or a zony, zebra and pony. Wait, let me check. Is there any page for source in this website? Am I liking? Oops, error, okay. I guess not. But yeah, this is something new, I guess. And that makes me wonder why. Is that for only experiment? Yeah, I'm not sure. But Sonki exists. Okay, the cross between zebra and a donkey. I didn't expect that I will learn that in an operating system book, you know. But yeah, that's quite a surprise, I guess. Thank you, the author. Okay. A multi-level page table. Oh, right. A different approach doesn't rely on segmentation. A different approach doesn't rely on segmentation, but attacks the same problem. Okay. Previously, we combined the the patching and segment, right? But the problem with segment is that we have we didn't have the fixed size for the segment, so it become it introduced the external fragmentation again. So that is the problem. This hybrid causes external fragmentation to rest again. While most memory is managed in page size unit, the page table itself now can be an arbitrary size. Right. The page table size now have a variable length size, which can change, I guess, or arbitrary size, and that can cause external fragmentation because we might not have enough space for a new page table, something like that. And then this is another attempt, I guess. A different approach doesn't rely on segmentation, but attacks the same problem. How to get rid of all those invalid regions in the page table instead of keeping them all in memory? How to get rid of all those invalid regions in the page table instead of keeping them all in memory? We call this approach a multi-level page table. Okay. Previously with the linear page table, I think we are still storing those invalid page, right? For example, where is it? I guess this one. The valid bit 1 means that it is valid and 0 means it is invalid. But the entire page table, even the invalid one, is still stored somewhere in the memory. Not only the valid one. And that can take a lot of space, especially if we have a big address space, right? Like 32-bit address space. If we check here, it is around 4 gigabyte, I guess. 4 gigabyte address space. And if we need to store all of those 4 gigabyte page, that can be a lot of waste memory, I guess, something like that. And keep in mind that each process have its own address space. So if each process need to store 4 gigabyte of page, that's gonna take quite a lot of memory. Okay, how to get rid of all those invalid regions in the page table instead of keeping them all in memory. We call this approach a multi-level page table. As it turns out, the linear page table it turns the linear page table into something like a tree. Turns the linear page table into something like a tree. Okay, this approach is so effective that many modern systems employ it. For example, x86. We now describe this approach in detail. Okay. Well, you know what? I guess let's continue this on the next session. Yeah, I'm not sure if I can analyze this in the current session. So yeah, let's continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.